do basic circuits.
It's basically.
I don't know why they make you wait till physics too. Well, I do know, because it's about
See, that was door.
for organizational purposes, but.
That's already. Oh. Okay, I was on that door. Yeah, no, it's like, you're at two. Yeah. You're the one that's right? Yes. You're the one that's right. I'll show you how to do like the. Yeah. Sorry, to do some. Computer. I didn't show you. This one. So, okay, this lecture is for the wind tunnel. Everything, every theory that we have to know, just bite-sized information, because the main part of it comes from building. I don't want you guys to just like be heavy on this lecture. So, what's a wind tunnel? This is an example of a wind tunnel. It helps us test the airfoils. It's the particular shape of the wing. We can also test like our plane models in the wind tunnel. We can test everything. But what's really good about the wind tunnel is that we can test it at any pitch. We can test any type of airfoil that we want in different conditions, like turbulent flow, laminar flow. We can test at different pressures and different Reynolds numbers. So here, when you see a wind tunnel like this, uniform flow, that means it's laminar. I'm going to get into what that means in a little bit. And you can just see how like air flows around the shape, because that's really what aerodynamics is, just how air flows around a certain shape. Okay, so this is just like a little bit before we get into it. Before we had NASA, we had NACA, and that's National Advisory Committee for Aeronautics. This is solely on planes. We're going to get into a lot more of NACA designs in the fall when we go over aerodynamics and airfoils. Basically, they made everything that there is for us to know about aeronautic design, specifically airfoils. Any type, they came up with the nomenclature for it, how to make different types of airfoils by their density, their thickness, their length, and what they're used for. And NACA made a lot of wind tunnels too. So that right there, this was one of the early wind tunnels in the 1930s. It tested a lot of planes that we used in World War II and World War I, and you can just see how big it is by other people. After that, after the 1930s, we stopped using subscale and transient scale wind tunnels. We started going into more Mach speed wind tunnels, speed of sound and stuff like that. And that's where we get the Concorde. Now wind tunnels have to be a lot faster. Their testing chambers have to be a lot more smoother and stuff like that. And yeah, that's the type of wind tunnel we use today. Somewhere here, I think the third floor or second floor, there's a supersonic wind tunnel. I'm not sure where. And this is the Wright Brothers wind tunnel. Unlike most wind tunnels, it doesn't have like a testing chamber where you can see the laminar flow inside, or just like the airflow inside. So what they did is that they had like a little balance on the, like going through their tunnel, so that they put their model on, and if it became lighter when the air was flowing through, then lift. And if it became heavier, then you probably shouldn't test that. So, okay. This is the last slide, and then we get into like actually heavy stuff. There's two types of wind tunnels by design: open circuit and closed circuit. This is a closed circuit, this is open circuit. This is the Wright Brothers wind tunnel as well. But in a closed circuit design, there's no air going in or out. The air that's in there is just the air that's being tested, and it's going in circles and circles and circles. You have here the compression, where you're actually testing whatever model you want to do. The good thing about a closed circuit design is that you can control density, like the air density around it, and you can test it in different conditions. So like if you wanted to test a plane on Mars, you have to do that on a closed circuit design, not an open circuit design. Open circuit design is what we're going to be using. It's really easy to produce. It's not closed. Closed circuits need a lot of space. These don't. This is a Wright Brothers design. It had a balance here. So when they were testing their planes or their airfoils, if it became lighter, and their airfoil was generating lift. Then by speed, there's 4 different types of wind tunnels. You have subsonic, that's at 0.3 Mach speeds. You have transonic from 0.8 to 1.2 Mach speeds. Supersonic from 1 to 5 Mach speeds, and then hypersonic 5+ Mach speeds. For civil aviation, we're going to use subsonic, that's what we do, but for airlines, they usually use this. Okay, and this is heavy parts, the heavy part of the lecture. one of the first. So earlier I told you guys this Bernoulli's equation. Bernoulli's equation, this is what you see in physics. That's what we're using. It's a little bit different. You don't really have to worry about the potential energy because you're not putting, like if it's flying or if it's in a, yeah, you'll worry about potential energy. Our case, not. So let me see. Let's imagine we have an airport, the shape of the wing. Here, right? You're traveling at 30 miles per hour. That's what we expect the ultralight to go at. Air is hitting perpendicular or horizontally the airfoil. As air hits the airfoil and this airfoil begins to, let's say, has an angle of attack, it's angled at 2.5, an angle of 2.5 degrees. So it's a little bit more like this. Air starts traveling on the top of the airfoil. And as it travels on the top of the airfoil, it becomes faster as it goes on the top. As air travels on the bottom, air slows down a bit. Thank you. Air slows down. The faster that air travels on the top, the less pressure is here, becomes negative pressure. This becomes known as the negative differential, and that negative pressure differential and the speed of here causes lift upwards. There's high pressure here on the bottom from the low speeds of the aircraft. That high pressure also causes lift, but not as much as the high speed airflow. 2/3 of the lift is generated from the top of the shape, and 1/3 of the lift is generated from the bottom of the shape. That video I'll show you now so you can just see. So this was at the beginning of the presentation. It's basically what you see now. I ended. So let me speed it up to here so you can see what I was talking about. So air travels faster on the top of the airfoil than the bottom. That's what makes the lift because there's negative pressure on the top. That negative pressure is what causes the lift. And you're about to see the airflow. There's like a slow motion here. And you'll see that all these top ones go faster than the ones here on the bottom. See, they're just more ahead. Suppose these are slower. And that's how we get lift. So from Bernoulli's equation, this is really important for mechanical engineering. I know you two are electrical, you're mechanical, and you're also mechanical, right? And Andy's mechanical.
Yeah.
So Bernoulli's equation is really important for us when it comes to aerospace specializations, because this is one of the justifications for how lift exists. The higher speed means that there's lower pressure. This change in pressure here is what causes lift. Lift is just a negative pressure differential. You guys understand that? Because I know it's like a lot of big words, but Andy, are you?
I mean, yeah, I kind of understand what you're.
Okay, I just want to make sure because I know it's like it's a bit dense. This material is dense. It's not a secret. But yeah. Okay. So when we have lift, we also have drag. The more drag you have, the more lift you have. So like biplanes, planes that have two different layers of wings, early planes, they have a lot of drag, but they also have a lot of lift. That's generally why they decide to put two, like the Wright brothers and then later Barron's planes. And let's see. Yeah, so lift is just what opposes weight. That's when you get this thing off the ground, that's how paper planes fly, all that. And then when it comes to drag, there's two types of drag. You have parasite drag, and this is caused from the airfoil shape itself. So let's say you have a monoplane, right? Monoplanes kind of have a wing that looks like this. Let's just say it's a straight wing for now. These wings are going to generate here at the end more drag as you go down. This drag creates kind of like a vortex on the airflow, and this slows down the plane considerably. So in order to stop this, what we've done, and you'll see this in like airlines, they have winglets. So you have like the plane here up front. you have the wing, but you have these things pointing up or down. And this, instead of the airflow going down and like having a vortex here, it causes that drag that's happening to cause up here. This is on some planes. The plane wings that we have in the makerspace are elliptical, so you don't really have this issue with them. It just gets dissipated out as it goes down. So there's parasite drag that's generated from the airfoil shape itself and the surface. So let's imagine you have a rough surface, something like wood. You're using just a completely wooden plane. You haven't coated it in ultra coat, paint, anything like that. And it's really rough. That's going to create friction with the air as it passes through, and that's also drag. Then you have induced drag that's caused by lift generation. So as the plane starts going up and up, it displaces more air, and that air that it displaces is drag. So if you ever go to Miami International Airport, you only see commercial and cargo planes there. They're huge, they displace a lot of air. But you're never going to see like a small Cessna, because if a Cessna were to go off the runway at the same time as a commercial A380, let's say, that Cessna is going to get ripped to pieces from the air that's displaced. Genuinely, it will fall out of the sky. There's not, it's horrible. That's why we have specialized airports for smaller planes like Opa-locka and Tamiami. Miami
Yeah,
Executive.
Tamiami. Well, it's the same deal.
Okay. So here, this is just some ways that we can like test at a specific point the force that's being affected on a plane. These are load cells. We have one in the makerspace. I'll bring one next time. Or next time that we do something, I'll show you guys. But yeah, these load cells basically just measure the amount of force in a place. The lift across the airfoil is not uniform. I'll show you guys that inside. Okay. So this shows the amount of pressure happening on an air. Actually, let me lift this up. This shows the amount of pressure on an airfoil as it's traveling with a uniform speed at a uniform angle. So this is called the chord line right here. It's the distance from the leading edge of the plane, the most farthest point, all the way to the tail. When we get into airfoils, there's a naming convention for this. So the airfoil we usually use is called NACA 4412. One of these numbers is used to denote how long the airfoil is itself. Another number is used to describe the thickness of the airfoil and so on and so forth. But as an airfoil is traveling, as a plane is traveling, you have higher pressure here up front, and that's causing 2/3 of the lift. And then you have, because you have a high speed of airflow up here, then you have low speed airflow, and that's high pressure up here, right? This pressure here and the pressure here contributes to 1/3 of the total lift, and this contributes to 2/3 of the total lift. That's just like an estimate. Each airfoil is different, not each one is the same. But if we go down, this is Reynolds numbers. So Reynolds numbers tells us the type of flow in a system. So the higher Reynolds numbers that you have, the more airflow you have, the higher speed you have, the bigger you're testing, right? So while a commercial plane.
What? Oh no, sorry, I was just.
So like a commercial plane could have Reynolds numbers in the millions or billions, while a Cessna is probably somewhere in the thousands. To test Reynolds number itself, that's the equation that we use. It's just the airflow, the density of the airflow. Rho is density. Sorry. It's density times the velocity times the characteristic length. For this case, characteristic length is the camber line. It's the distance from the leading edge all the way to the tip. And that's divided by dynamic viscosity. That's just how air separates from itself. So, okay, I kind of dirtied this up. When we're dealing with planes, and this is why we really need to use the wind tunnel correctly, you have an airfoil. So you guys already understand that for there to be lift, air has to travel on top of this top surface. If air isn't on this top surface, then there's no lift.
Mhm.
When you increase your angle of attack, the air flowing on the top becomes less and less that reaches the bottom of the trailing edge, right? So there becomes a point where all the air that's traveling on the top only reaches a certain part of the airfoil, let's say here, and doesn't reach anything here. When that happens, that means that a stall is starting to happen. So if you've ever seen a cockpit, for example, you'll see stall warning, stall warning, stall warning, pitch up, pitch down.
Oh, okay.
Because once air is no longer traveling on the top of the airfoil, you've lost 2/3 of your lift and you're just going to start falling from the sky. And then to break a stall, it's a lot more difficult. So, yeah. So for our wind tunnel, there's a considerable range for the Reynolds number. When we use XFLR5, we can use any Reynolds number we want, any pressure we want, any air density we want. But our wind tunnel is, right, it's much smaller. It's not gonna. So laminar flow for a wind tunnel is any Reynolds number under 2,300. Transient flow, that's okay. I guess I should describe this a lot better. When we have a wind tunnel, this is our testing chamber. Laminar flow is straight flow. It's undisturbed, it's controlled, it's uniform. Transient flow is a little bit disturbed, but it still follows like a uniform path, kind of, right? And then turbulent flow, that's generally what we don't want. It's just it going in any direction at once. And then we don't have, if we find turbulent flow in our wind tunnel, that means any data we collect from it is invalid. We just can't use it because that's not, even if you were to throw this marker at someone, it's going with the laminar flow or at least turbulent flow. So that's what this describes. Good. So yeah, okay, this is why wind tunnels are important. Basically, if we use the right wind tunnel and we scale the right Reynolds number, so if we have a small, we're trying to test our plane design, let's say if it's the ultralight, it'd be like, the ultralight would be the distance from here, this desk, to here, as of now, that's the expected ultralight length. If we'd want to scale it, it'd be like a 10th scale, or even smaller, maybe a 20th scale for it to fit in the wind tunnel. When we scale it down, we also have to scale it down with the Reynolds number, right? Yeah. So a bigger Reynolds number is aimed for a bigger plane. Smaller Reynolds number for smaller planes. So if we can use the right Reynolds number with the right scale of the plane, we could basically test the plane as if it were like as big as possible. But that's important. So here is basically like a video on stall.
As the angle of attack of an airfoil increases, the flow in the boundary layer stops, then reverses direction. This is called boundary layer separation. As angle of attack increases further, the point of separation moves forward on the airfoil until it has so disturbed the flow around the airfoil that further increases in angle of attack produce less rather than more lift. In this condition, the wing is said to be stalled.
See, and air is just not traveling on the top surface anymore. And then it just falls out of the sky. So Air India, that plane stalled. It's very unfortunate, but that plane stalled. Can look it up. There's hundreds of examples of planes stalling. David from Boeing. You guys met him?
No,
No.
he was on parental leave last time.
Yes. Yeah, that's right. Okay. Well, David from Boeing, he's a flight test engineer. You guys are all going to meet him hopefully in September or October. Because for Boeing Week, he comes here. Or, yeah, in September, we're going to meet him because we have a workshop then with him. But he's a flight test engineer. So what he does is that if you ever go into a plane that's a flight test is being performed, you're going to see these big barrels of water all connected with pipes and everything going crazy. And what they're trying to do is change the center of balance on the planes and see when it will stall if you're carrying something here or there, or if you shift the center of balance all the way to the back. If you shift the center of balance to the back of the plane, you're just gonna start doing backflips in the air. So you just, remember that you're never gonna. And then this is just like a video from like British Air Force.
Your
that they did
aviation testing.
early, very early wind tunnels.
That's my favorite instruction to remember. Sounds of wind in the tunnel are controlled by the experts who observe the behavior of the plane, work out the best method of making it behave better.
Yeah, so pretty much it. It's a vertical wind tunnel, not horizontal. So basically what they're trying to test there is where the center of balance is. Our wind tunnels are more to test where our plane is going to stall and if our designs are aerodynamic or not. So, okay, these are different types of equipment that we can use in the wind tunnel. At the moment, we're really only going to use a force balance because that's what we have in the makerspace. We also use the force balance for propulsion testing. It's what helps us like tell the amount of thrust that it's producing. So this is an example of force balance. It's just a regular balance with a pin connecting to our plane, our airfoil, what have you. This helps us tell us the amount of thrust and the amount of drag that's being produced by our design or whatever we're testing. This is a static pressure measurement. It's basically just an airfoil with a bunch of holes in it, a bunch of little holes measuring pressure. This helps us tell where lift is happening and where it's being generated at a certain point. This is a pilot static tube. This tells us the speed, the expected speed of whatever we're testing at whatever speed we're testing it at. And then this is a total pressure measurement. This is just supposed to tell us the pressure within the wind tunnel once it's closed and once it's being tested. And then this is our wind tunnel. This is what I have planned. This is what I was given from the Wall of Wind people. This is basically how they work. Let me lift it up one more time. Wow. So in a wind tunnel, starts from here and ends all the way over there. You have a big fan which is causing turbulent flow, right? So in order to correct that, we have these flow straighteners. Right now we're going to use snap tubes for these. As you have turbulent flow going inward, right? The flow straighteners correct the flow going into the wind tunnel. And then as it goes down here into this contraction, since it's getting smaller, remember Bernoulli's principle. Over here in Bernoulli's principle, this equation doesn't really describe it well. Think of just a hose. When you make a hose, when you like press it down, the flow of water becomes a lot faster, right? The same thing happens here, where when this contraction happens, even though this is going maybe 15 miles an hour, once it goes down here to this contraction, it could go 30, 45, maybe up to 50, depending on the speed. And once it goes through these flow straighteners, the flow is laminar. It's no longer turbulent. So then we can control the flow of the air, and as it passes through the contraction, it stays as laminar flow. One difficulty that we have with a fan is that a fan produces what's called big eddies, right? Turbulent eddies. It's this big type of drag, vortex, right? Just a vortex. And that we can't have that in a wind tunnel. That would invalidate all our data, and then we'd have to, just ignore that, all of that. So as it passes through this is called the working section. This is where now we start to put all of our measuring equipment, all of our stuff. So one thing our wind tunnel is going to have is smoke injections. Here is where the smoke will be injected from like a very razor thin tube. The smoke will be traveling with the laminar flow air, and it's going to travel, it's going to continue in a straight line. This is our test sections. So here's where we'll actually be putting our airfoil, our plane design, what have you. So let's say we're testing an airfoil because it's easier to draw than plane. So as we test our airfoil, we can just like have a small connection down to the ground. We can connect it to the force balance, and that will tell us the thrust, it will tell us the lift, sorry. And yeah, This is another test section. From here, we can have more instruments. We can have the pressure gauges and others. And then this is where we already stop. This is where we stop. We don't have, this shouldn't be open in any way. This shouldn't either. This is a working section and this is our diffuser. So as air travels back out, in order to keep it laminar here in the test sections, we need to reopen. And as this reopens, it's no longer laminar, it's more transient airflow. So Reynolds numbers of 2,300 all the way to 4,000. And it just goes back out and it goes from speeds of 30 miles an hour back to 15 miles, just like a regular fan. And then it just goes back out to the environment. It's open circuit. Okay. So they're pretty important, I guess. I just include interview questions. So you guys want to answer them or you guys can choose anyone? They're just like interview questions someone might ask you about these projects. Stuff you can mention in interviews. So which one do you guys want to do first? First one? Okay, so how does Bernoulli's relate to data collected in your test section? Does anyone know? Take a wild guess.
Well, isn't like the whole point, the pressure differential is what causes the upward lift?
Yeah. So for Bernoulli's principle is the very heart of aerospace aeronautical engineering, right? Without Bernoulli's principle, we don't have lift. That's one of the arguments for lift. The other is Newton's laws, but it's the same thing. How do you ensure flow uniformity and minimize turbulence? We have the flow straighteners for that. Some people use a honeycomb design, other people use cloth in order to ensure that flow is going straight. We have flow straighteners, and then as it goes out, we have the diffuser section to ensure it can go out transient and not turbulent. And then what is the function of the contraction section of the diffuser? It's just to return the air to where it was. So I included the answers to all of these as well. So Bernoulli's principle explains how fast airflow leads to lower pressure, and that's, yeah, basically what you said ends up. And it helps us, in this case, we can test any angle of attack that we want. We can test any conditions that we want. So I'll give these, this is just a summary. Wind tunnels are what we're going to use to test small scale planes in a real scale environment, like, because we're not going to be able to test an ultralight several times. Ultralights are expensive. So what I would say, ultralights are expensive. We really can't afford to keep building it again and building it again and building it again every time it falls out of the sky. Yeah. Right. And yeah, okay. Pretty much everything. Have a Kahoot. Mr. Worldwide. How many times did Mr. Worldwide show up in the presentation?
Once at the end.
Once. Okay. I just want to make sure.
What are like the big aerospace companies that hire from people from this club?
For the most part, it's Boeing. I've asked 13 alumni, 10 of them work for Boeing. They work in flight. They work as flight engineers, so they test where the center of balance is on planes. They test all the new planes. Some of them, they work Ryan. You'll also meet Ryan. You've met Ryan. You got a patch from Ryan.
Yeah,
Yeah.
yeah.
Ryan, he works for Phantom Works.
Yeah.
Do you guys know what Phantom Works is? So, okay, Lockheed Martin has Skunk Works, and Skunk Works makes all of the military planes. They made the B-2, the B-2 bomber, they made a lot of bombers, a lot of stealth planes. The defense side of Boeing is called Phantom Works, and they made the F-16, the F-15, they made all of those series. The only plane to shoot a satellite
Yeah,
in space out of the sky.
they're making a new one that's supposed to come out soon, and apparently it lets the pilot like using AI to like mind control 8 like drones while he's in the plane.
Yeah.
47.
I think so.
And there's also the reason why we're having you guys are already in.
Yeah.
How's are you gonna? Okay. The reason why we're also building the UAV in the fall is because a lot of defense companies are trying to build UAVs. I'm not sure if you guys have seen it. There's a for also I think it's also Boeing.
Probably.
3 UAVs go ahead of the pilot to just reconnaissance and all that
Yeah,
stuff.
yeah.
Obviously, our UAV is gonna be very simple. It's not gonna shoot anyone out of the sky. I don't even think we can fly it over flag or street because then we're gonna like cause
Yeah.
definitely an accident. So everyone's in okay.
Yeah.
Guys. So remember, there was two types of drag. Parasite drag, and that's caused from the shape of the airfoil, the material that the airfoil is made out of, and then there's induced drag, right? The drag that occurs as the plane is going up and up. Drag that's formed from the disk. So remember, the test section is a smaller part of the wind tunnel. It's after the contraction. For this example, think of like a hose. When you like press down on a hose, the flow goes faster.
It's like the cross section of the wind flowing.
Oh, okay, that's great. That's like the main part. That's really the main focus of this presentation.
No one's getting hired by hearing.
Yeah, everyone here is getting hired by Lockheed, don't worry. So it might be nice to have the Reynolds number. So remember that Reynolds number is the fluid density times the airflow density times the length of the model divided by dynamic viscosity.
I thought the fluid density was that. I blew up the plane. My bad. I had to go.
That's also really important. That's why I really tried to emphasize the Reynolds number. We're gonna go into a lot more depth about this in the fall. I just don't want to go into depth about it now because it's summer. You guys are all gonna forget about it. And we still have to do this in the fall, so we still have a lot more time. Oh, okay, that was really fast.
Everyone going here and use.
Wait. No, this should be true.
I'm winning the coup, I don't care.
This should be true, I'm sorry. Let me see if I can change that.
Nah. I beat the system.
No, that should that one should be true. That should have been true.
What's the question?
Force balance, like the measurement, like the tool for measurement. What does it measure? Does it measure both lift and drag? Does it not measure? Does it measure one or the other?
I think.
Yeah. Okay. I asked this already, but
How many times you showed that by you? 0. It's twice.
twice.
Well, it's the second time.
Hold on. I honestly was.
That's one.
That's one.
Oh, I see.
That's
Oh, wait.
you can see it like very vaguely here. I'm not sure if you can like.
Yeah.
That's not true.
So twice. Okay, we have it twice. Oh wait, let's see who won.
Well, I got the wrong question right.
Yeah. Sonja gets last.
Nah.
Okay, I'm gonna
Wait,
give
what was
you-
the question again that I got wrong? Right, that was wrong.
It was the pressure differential. So there's greater, whenever lift is being generated, there's greater pressure up here than there is on the bottom shape, on the bottom end of the airfoil. That said, it said the wrong answer. So, yeah. Okay. Do you guys have any questions?
Wait, can you go back to like the pressure differential thing?
Okay. So, pressure differential. Let me go to the side that has this one.
So because the higher air velocity on top causes more.
Yeah,
pressure.
so let's focus on Bernoulli's equation, not this one, but that one. Let me just erase a little bit, have some space. Bernoulli's equation, the one I wrote up there, is pressure plus 1/2 density velocity squared is equal to a constant. This constant only represents the energy that's present in the
System.
wind tunnel system, yeah. This is pressure, this is air density, and then this is airflow speed squared. If you guys remember anything from physics 1, this is just energy, right? It's just mass velocity squared, it's kinetic energy, 1/2. So, what was the question?
Oh yeah, so you said there was a greater pressure on top, but wouldn't the pressure lower if the speed is higher?
So, yeah. From this equation,
So if there's lower pressure on top.
yeah, so if you have higher speeds up here, you have lower pressure.
Wasn't that the Kahoot question? Or did I read it wrong?
Let me see.
It's false.
Give me a- Pressure on the top of the airfoil is greater than pressure on the bottom when lift is being generated.
Wouldn't, yeah, isn't that false? Shouldn't the pressure on top be less?
Pressure on top is.
Yes. Yes.
So that is,
Yeah, okay. Oh my god.
Yeah,
yeah, sorry, I'm not getting higher by here.
yeah, it's due to the velocity. You have more velocity on top.
Yeah, it's the wind's faster on top.
Yes.
You have more velocity.
I'm going crazy. I'm sorry. I made these last night. Okay. Why great? Yeah. So the faster it's going, remember if this is just the constant of energy in the system. So we can move this, or let's just move pressure to the other side, right? You would have velocity is equal to negative pressure. So velocity is proportional to the pressure going down. As velocity increases, pressure decreases. Faster airflow up here, less pressure, and the faster that air is flowing, the less pressure that there is, the more lift is being generated.
Yeah, I understand that. I was confused.
No, yeah. No, I'm sorry, I'm going crazy. But that should be, any more questions?
Oh, what are we gonna build the wind tunnel out of?
It will be a 1/4 inch foam. 1/4 inch foam, and then let me see if I have it here. Yeah. Here's actually all the 2D designs for the wind tunnel. This is from the Wall of Wind. The Wall of Wind isn't a wind tunnel, not the type of wind tunnel that we use. They are a wind tunnel, but it's used for civil to test buildings. It's not for planes, it's not for cars, it's not for anything like that. Okay, they use hurricane winds to test their buildings, see if whatever structure that they build is stable, like they can handle Florida.
Right.
But yeah, so there's just gonna be like a regular 3-speed box fan. That's what generates the airflow. Then it goes into the flow straighteners, or just gonna be like carton snap seal tubes, just like a carton pipe. That's gonna go into the contraction, and then from the contraction, here's where we start actually putting in our tools for measuring airflow, for measuring pressure, measuring all that. This test section here is gonna be one glass face, so we can actually see the airflow. We actually know what's going on inside. And then this last test section is just gonna be foam again. That's where we're gonna put tools to measure like the flow as it goes out and all that. No, wrong one. So yeah, any other questions? And then look, to your point, Enzo. Try to. This is just slower. Here it's already faster on the top, and that's how you get lift. Then this that's going slower here on the bottom. Yeah, so that's that. Yeah, and then here you have pressure. This green part and these red also show the pressure that's being formed by the airflow. And all of that turns into this lift. Any other questions? No? Okay. So I'm gonna send this in the group chat. You guys are gonna have a lot of different more resources where these go into actual depth about every little part of this. I know I didn't, I was going like a little bit crazy, but all of these videos go into depth about how lift is generated. This one is a professional wind tunnel at University of Washington. You guys should watch it. They go into a lot of depth about how they actually collect data, like raw data from wind tunnels. It's a closed circuit wind tunnel, so it's like a huge building the size of EC. So this goes into like how lift is generated, like the actual depth of the formulas. This is all too much information to go over here because this summer I'm not gonna.
Yeah.
Wait, so for actual data collection, does the force balance have all of that built into it, or do we have to put?
No, the force balance, I'll show you guys next time. You've seen it before. It's like that big, you've seen the propeller that's connected to like a stick kind of.
I think I have, yeah.
It's a deflection shield. So depending on how much is being deflected, we know the amount of thrust, and from there we can determine the drag. All of that's collected through an Arduino, and that Arduino just returns to us the values. So the other option is just using like a regular balance, and that will tell us like a balance in pounds, because pounds is a unit of force, right? So that will tell us how much lift is being generated from that scale. And then these are just the other videos. This just goes over from like a pilot's perspective, how lift is generated, what to do in a stall. This is how, like, from equations, from Bernoulli's equation and Newton's third law, how lift is generated. And this just goes into drag, like different types of drag and all. There's another video here. The one that should be here goes over Reynolds numbers. But that's, yeah, that's pretty much everything. I don't know. You guys are just
Yeah.
staring at me now. Yeah, okay.
Thank you for pressing.
So it's lecture. Hey.
Now we're flying.
Oh, another one on Friday.
Hmm?
We have another one on Friday, another lecture.
No. Oh my god, no.
For
Next
the
Friday, we're
night.
building the wind tunnel. Building the wind tunnel. Not gonna like put it like that. Yeah, okay. Oh wait, can we take a photo in front of like everyone?
Yeah.
Alright. Is everyone okay with that?
Oh, yeah.
We learn. Yes, we learn. We have to have more lectures throughout the year, but we're actually gonna focus on depth about those things. Like how we actually use wind airfoils, how we choose our airfoils and stuff like that. I don't know if you guys are just saying,
No offense. Single pipeline. That's all. It's a white pipeline.
I'm just staring. I'm like, oh, okay.
We're taking a picture to commemorate this moment of learning and understanding cool and passing the quiz.
Yeah, everyone passed the Kahoot, I guess. I don't know. I should probably
I'm gonna have the
everyone like get a lot of
the projecting all over this.
Yeah, good.
oh, what's it? Okay.
Now you put something on Instagram for once.
So there's.
Yes, yeah.
To get the.
Oh, makerspace certifications. Jose, ¿tú te acuerdas que ayer te estaba hablando de como the rocket engines, they had like that thing?
Yep.
It's called an aerospike.
certification.
Aerospike.
Yes.
Búscalo. It's like,
I don't think so.
Eric,
Yeah.
for the certifications, do we have to redo them like this year as well?
I'm gonna show him the certifications now. Yes, you guys have to do three certifications.
Again?
Yeah, because there's some that